Thank you. Good morning, everybody. And thank you very much for coming to hear my talk. And thank you very much for inviting me to come and talk. And I, as Peter said, started off as an anaesthetist. And so I started for the European Society of Anesthesiology, a Teach the Teachers course. And as we all learn in our basic teaching courses, the rules of how to teach. And I thought, well, this is all very well, but being a scientist, I'd like to know why those are the rules and what is the science behind all these things they tell you. Because a lot of my research colleagues would say to me, oh, teaching, anyone can do that. And they would say, oh, it's just soft science. There's nothing behind it. And I thought, I bet there is. So that's why I spent quite a lot of time working out what the neuroscience was behind what we tell you when we want you to teach. So I'm going to start off with, talking about, so what we want to be is effective teachers. Yeah, we are all subjected to a lot of teaching from the first grade in school until you graduate from your university degree. You are taught all the time. And so we're sort of like Manchester United supporters. Now, Manchester United supporters, they think because they watch a lot of Premier League football, they know how to play Premier League football. And mostly they don't. Mind you, neither does Manchester United at the moment, but that's another story. And it's sort of assumed that you can teach because you've been taught a lot. That is not actually the case, and I think you'll agree. We want to be effective teachers, so we need to know the rules. So we have to think about adult learning. Adults and children are different, and I know this from experience. We're talking about teaching people who are undergraduates or postgraduates, so therefore they have got this body of experience behind them, and they're starting to learn in a different way than young children. So we have to think about what is learning. What are we trying to do when we get people to learn? Well, we want them to acquire knowledge and skills, attitudes and behaviours, but we also want them to be able to use them. We want them to have these as their primary way of behaving. And so we want to change in their behaviour. So learning isn't just learning a list and repeating it. It's about how we behave in the light of this new knowledge. And this is particularly important for us because we're teaching people to do practical things. We don't want to sit in the corner and recite a list of the possible diagnoses. We want them to look at the patient. We want to change their attitude, change their behaviour. And for us adults, it's going to be built on what we already know, because we have a basic from our basic science training, we have some understanding of what's going on. And so we're going to take every piece of education we're given and consider it in terms of what we already know and decide or work on how we change our behaviour. And it's also very important on the setting, what we do as we learn. What we do as we learn is much more important than people realise. Okay, so what is teaching? This is a really nice description of what is teaching. And the most important word in this sentence, does anybody want to tell me what they think is the most important word in this sentence?
Change.
Change, yes. Change, planned, thank you. That was the one I was wanting. Because we have, a lot of us, people my age, learned by just being thrown in at the deep end from experience. This is not a very efficient way of learning. And much of what Jason was saying already about his information feeds very well into this, because we have to plan the learning experiences of our trainees using all the modalities we can appropriately. And then if we plan it, it's more likely to stick, and stick the time too. Right, so here's a nice slide. I just want you to read this. Okay? I taught him. I didn't say he learned. And our job as educators isn't just to spread information in a rather exciting fashion, but it's to make sure that that learning, that change of behaviour has taken place. And we tend to be quite bad at that. We do assessments, but we haven't really looked at behaviour change and how we can bring it about. Children, as I said, learn differently. I teach children to sing as part of my other life outside medicine. And I am always amazed by their ability to absorb information. It's like they're like sponges. They're aged between 8 and 13 when they're learning to sing, and you tell them something, and then the next week they say they know the answer. They've remembered because they have lots of capacity for learning. They're learning at a basic level, but they have lots of capacity for learning. Adults learn much better by doing, by engaging, and as we see in the right-hand picture. And so when we're thinking about learning, we have to think about how we engage them. So let's think about what's happening in your brain when you're learning, because after all, that's where it's got to go. Most of what you remember is in your prefrontal cortex. This is why people who have bad head injuries, frontal head injuries, often have memory problems. And the prefrontal cortex is the key place where it's kept. But there's an important interaction between the prefrontal cortex and the hippocampus. And you have to have both intact to be able to make memory and also to be able to recall it. And we know we're quite interested in how we recall memory because of the implications for aging, me particularly, and what happens to your memory as you age. But what we're interested in as educators is getting that information into the prefrontal cortex. So we can divide memory up into 4 different processes. First of all, you've got to take the information, what's coming in from your sensory cortex, from your eyes, your ears, the haptics, your touch, everything, and you've got to encode it in some way so that the brain can hang on to it. Okay? And then once you've encoded it, you're going to have to consolidate it and put it into long-term memory so that you can keep it for later. And you've got to have a storage system. But what you need is to be able to recall it, because you can store it and not recall it, and that's not helpful. And we've also got this phenomenon of forgetting. We've probably forgotten more experiences than we've remembered. And so there's some kind of system going on in the brain which is saying, I don't want that one, throw it out. And we're not an unconscious one we're not conscious of. Quite a lot of science has been done on encoding and a little bit on consolidation. Storage is almost completely speculative. And recall is becoming interesting because recall is, as I say, part of degenerative disease of age. And it turns out that it's very involved not just in the neurons, but in the microglia in the brain as well. So let's look at them in order. If I'm doing something and I'm giving this talk and I'm trying to make a memory of this talk in my brain, all sorts of stimuli are coming into my brain as I'm doing it. I've got the pictures, I've got your faces, I've got the temperature of the room, I've got the clock over there ticking away rather alarmingly, I've got the chaps at the back looking at me anxiously because it's not necessarily, sound isn't working properly or whatever. All of that is coming into my brain. So at the moment, I am in a state of high alertness. I'm attending. I'm not thinking about what the dog's doing or, whether the plane will be late. I'm thinking about you. I'm very concentrated on here. And so everything that I'm seeing now or experiencing now is going into my immediate memory. And it's very strong. Yeah. And I will start to put things into working memory. And I will do that 7 objects at a time. So when you're taking out of the experience, when you're trying to get experience into people's brains, shall we say, you have to plan it so that they have 7 to 10 objects in a time period. Because that's about all you can manage. If you give them more than that, you're going to get cognitive overload and their memory will not form. Okay, so when we're planning our teaching, we're looking at time periods and we're looking at numbers. We're also thinking about the time. So in 10 minutes, you can put new material of 7 different objects, and then after that it starts to fall off. So what do we do? What do we do when we've got to 7 objects? Because you've had 7 objects now, as you might realise. That's why I'm asking you. I'm changing the stimulus. So what can we do? Take a break, exactly. We can take a break, we can change things, we can do, I'm going to ask you to do something now. I want you to all stand up, please. I want you to turn round 3 times. And I want you to sit down again. Okay, so everyone's brighter, everyone's more interested again. And that's for 2 reasons. One is because it's funny and it's rather amusing. The second is because the proprioceptors in all your joints are fired off. And so proprioceptive information has gone up to your brain, which is part of the alerting reflex. So you're more alert. So we can use the underlying science to make a way of making our talks more interesting and our learners remember more. So once you've got it in your immediate memory, you've got to put it into working memory. And working memory lasts for longer. Your immediate memory lasts for about 10 minutes. Your working memory is going to last for up to days, and if you're lucky, weeks. But then to get it into long-term memory, which is weeks and months, that's another process, another reorganization that needs to go on. Okay. So we've got some, we know, it's not just a singular process in the nerves. It's influenced, as you would expect, as the brain always is, by lots of other things. So first of all, if you're tired, you're less likely to learn. And that's not an uncommon experience. I'm sure we've all been in that situation where you've been up all night and you've been to a tutorial the next morning and you've sat there and you've stayed awake and you've got through it and you've gone home. And can you remember anything about it? No, of course not. It's much more difficult. And it's also reduced by other aspects of a busy life, such as hunger, anxiety, and distraction, and also fear. And I think this is a really important thing because lots of our trainees are learning things in a state of fear. And that's one of the most important things about simulation is we allow them to learn what could be a very, very crucial clinical aspect of their work without the fear that they're going to do damage, which is why it's very, very important. So let's have a bit of a look at this. What's going on underneath? When you ask somebody to think of something, when I say to you, think of your house, think of a house, you're going to think about the house you live in now. And that's because you've got a very complex assembly of synapses in your brain which are storing the memory of your house. If you're 5 years old and you haven't really worked out that your house is your home, you might think of a cartoon drawing of a house or something that you've seen in a book, which is a much simpler assembly of neurons. And these assemblies of neurons are called engrams. And it is possible biochemically to identify engrams in the mammalian brain, not only to identify them, but also to mark them and to look at their activity. So it is possible in a mouse model to actually have a mouse which is set up with viral vectors put into it so that these assemblies will light up. And you can expose the mouse to something, fear, a shock, something, and you can see using photoprobes which part of their brains are alert, where those engrams are forming. It's the result of about 25 years of the most amazing biochemical work, but it can be done. So we're now beginning to understand a little bit more about making of these engrams. So these synapses are the important part of it. At this stage, at the early stage, getting early memory in, synapses are really important. And the strength grows as you have more connections. So the plasticity of the synapse, the synaptic arrangement, that it can get make more synapses and it can get stronger, is how you get from immediate memory to working memory to long-term memory. So, and it's got to be a really clever system, because you want to take things in a few seconds, and you want to have them still in your brain and recallable when you're 50. So that's a very complex and very clever system. So we understand more about the taking in than we do why you can get it out when you're 50. But we do know that it's a two-mechanism model. One is that you get immediate changes in proteins in the cells, and it's through a calcium glutamate model, which is not an uncommon biochemical model. And also that there is a genetic element to it. You get what was called epigenetic changes, so that in early intermediate genes in those cells are released, and they then can make structural changes, more dendrites, so more synapses, and changes in the storage patterns in the cell. So it's really quite, it's a very clever system, as you would expect. And we're starting to understand a little bit about it. So let's all make an engram. Right? I'm going to tell you some facts on this slide. This is my hospital, University College London Hospitals, and we have a simulation centre, not nearly as nice as yours, but we do have one. And our simulation centre is based mostly on postgraduate training, because the University College, has its own undergraduate simulation centre, which is also not as nice as yours. And we had, some years ago, it's quite a long time ago now, we decided as policy to introduce the WHO surgical checklist. Okay. And so we thought, well, you know, we can just put them in the theatres and hope people will fill them in. We can have a lecture about it. Or what we'll do is we'll take our teams of theatre nurses, anaesthetists and surgeons, who all work together every week, to the simulation centre, and we'll act out some scenarios where doing the checklist saves a disaster. Okay, and then when every team had been through, we introduced the checklist into the theatres themselves. And then we audited after 6 months how many of the forms were actually filled in for the operations. And we got a very, very impressive 90 to 98% completion of forms. Ask me how it's fallen off, and I can tell you about that. But that was how we did it. Now, I'm telling you that's your engram. Your synapses are working away, making connections, thinking, yeah, we know about operating theatres. Yes, we know about simulation. And we'll see how long your engram lasts. So I also said, as we discussed briefly, we have to think about other things as well as what's happening in the biochemistry. Because in order to get people to retain this information over a long period of time, they need it. If you don't need it, you won't remember it. I am sure when I was at school, I was taught something about the history of the 18th century in Great Britain. And I don't need it, and so I don't remember much about it. Occasionally, something will come up in the news that hails back to that, but mostly I don't. We need relevance, obviously, because we're teaching adults. They need to know why they need to know this. We need motivation. And these are all complex constructs which are partly stored in the prefrontal cortex, but also involve other parts of the brain. And we also need the capacity to learn. And that also involves how you are physically and whether you're willing to learn. So you've all made your engram now of my little hospital and its simulation centre. But I'd like you to remember it for a long time. And so we want to know how you're going to recall it. And sadly, we know very little about this. We do understand that those activities can be simulated by certain cues, particularly where you made it and how you made it and how you were when you made it can all be cues. So that's why it's really important that the fidelity of your simulation is important, because if you make it in a very lifelike way, when you need to use that information in a clinical situation, the cues for recalling the information are better. We don't know really why we can't recall. And we think that people with amnesia may have memories made that they just can't recall. And certainly we know that in the degenerative old age diseases where people's memories start to fail, we know that amyloid builds up in the cells. We know that other microglia cells around, supporting cells around the synapses are weakened or fall away. And so the understanding of it is very, very basic. But in 20 years' time, we'll know. Consolidation, which is the storage, what goes on with storage, means that you need to continue to use those synapses. And the more often you go back to that bit of information and you recall it, the more synapses are made. And so you are able to store that information. But for some reason which we don't understand, the brain doesn't keep them all. It leaves some of them available for further learning, which is a good thing because otherwise we would never be able to progress our learning from what we started off with. And this process is going on over weeks. And this is almost certainly where the new dendrites are forming and things are going on. The other interesting fact about it is that it doesn't just involve the neocortex. As I said to you, the hippocampus is important. And while you're asleep, the hippocampus and the neocortex are talking to each other. They're sending information back and forth. And this seems to be part of the consolidation process. And there is a theory, although we don't have the actual studies to support it, but there is a theory that what's going on in the neocortex is recording something that happens. And what's happening in the hippocampus is a time element is being added. So the when of your memory comes from the hippocampus. The what of your memory comes from the neocortex. Because you can have memories that aren't time fixed and others are. And this seems to be reorganized in your brain during sleep. So if you've had a really good learning experience, what you need next is to go to sleep and process it. Once we activate the engram, it's going to activate not just the memory, but it's going to have activate your emotional connections to it. So if you remember being frightened, I'm terrified of snakes, and I can remember finding a snake in my bedroom when I lived in Africa. And as soon as I remember that, even now, I can feel my pulses going faster because that was a very emotional thing. And so it also depends on the state you're in. And there is an interesting difference in gender because males prefer verbal cues and females are more sensitive to non-verbal cues to recalling information. Another useful thing to know. What was the name of my hospital?
Royal.
No, not Royal.
University College London.
University College Hospital, yes. What did we introduce in the simulation centre? Checklist, yes. See, that's more relevant, so you've remembered it. What about forgetting? What about forgetting? We lose information pretty quickly. Because short-term memory gets full, stuff gets dumped. If it's not put into intermediate or long-term memory, we forget it again. So we don't have any consolidation of that memory. And also the brain has has a capacity limit in terms of neurons, so that it's got to free up neurons for ones that you're no longer using. So you might lose things, you might forget things that have happened today, and you might forget things that have happened 20 years ago. This is a very interesting piece of psychological research which was done a long time ago, about 40 years ago, and this is the forgetting curve. Okay. So if you're given a piece of information, you get a very quick loss. You see, you couldn't remember the name of my hospital. Very quick loss. Didn't need to know it. Why should you remember it? After 20 minutes, you've got just over 2/3 left. At an hour, half of it's gone. And by 6 days from now, if you can remember a quarter of what I've said, I'll be really pleased. So how can we stop this? How can we do this? We don't want our medical students or our nursing students to go away and 6 days later have only got 25% of what we taught them. So we have this interruption. Well, if we keep going back to those neurons and reinforcing them, asking the questions again, the forgetting gets slower. So that you can see that if you have the original learning, gone. But by the time you get to the third review of the learning, the dropout is much slower. And so we have to put that into our plan too, because as we have come to an important point, the World Organization checklist, not the name of the hospital, we repeat it, and so we hope that by the time we get to the third time, nearly everyone will remember it for longer than 6 days. And so repeating and returning to information is a really strong and important part of getting this into our consolidated long-term memories. And it's doing it because it's strengthening the synapses. And it's because the brain is plastic and it can grow more synapses, more dendrites can grow more synapses, and it can organize itself. And this is happening over time. And by recalling the memory each time you do that, you're stimulating your engram to get bigger and stronger. So what does this mean in practice? Well, first of all, people have got to be comfortable and in a good state when they come to learn. Secondly, they've got to know why it matters to them. Relevance is really important. You can't get people to put things into their memory if they don't mean anything to them. And clear goals, as Jason also said, what will I have at the end? At the end of this learning that I've been to your session, what am I going to have at the end? That will dictate whether you move it into your long-term memory. And we know that feedback is a good form of consolidation. And we know that of interrupting the forgetting. And we also know that reflection helps to enhance long-term memory. And that is why, and my colleagues say, we never did that. I said, no, but you should, because this is how you get it into your long-term memory. So effective teaching has a scientific basis for planning, for supporting long-term remembering, and for enhancing recall. And I'll leave it there with you with those thoughts. Anybody got any questions?
Thank you. And any questions from the auditorium? Daniel?
Lesley, thank you very much for an interesting lecture. I think it gave us kind of out of the box view on what we are doing. And my question is, in one of the slides you said that in conditions of fear, our students will probably learn worse.
Yes.
And I wonder if we can change the conditions to a discomfort, whether this is something where we can focus our,
You have a U-shaped curve. Basically, you have a U-shaped curve. If you're unengaged and uninterested, you don't learn. As you get more attention, if you raise the attention and you raise the interest and the relevance, learning improves. Then you get to a point where you're frightened and you stop taking it in. And the idea is to try to get students into that sweet spot at the top of the curve where they're engaged and attending and understand what they're doing, but they're not frightened they're going to hurt somebody.
And that might be quite challenging if you have like 50 students in a TBL group.
Exactly.
And you expose them to a test and you want to get them into discomfort, not to comfort, not to fear.
Yes, it is. It is a challenge. It is a challenge. It's always a challenge to engage all the students. And there's always one who's looking into the distance. So and there's a whole science about how you can do that. Yes. Thank you, Daniel. Good question. Anybody else?
Another question? Yeah.
I'd like to ask, how does that mechanism influence or affected by the
how does that mechanism is influenced or affected by the information overload we are living in and the fact that we have all the information basically in hand?
Yeah, I think cognitive dissonance, which is what you get if you have information overload, is so common now, we almost live with it. If you want people to remember things, you have to dissect down. You have to keep things, not just keep things simple, but keep things focused, I think is the important thing. Certainly in skills teaching now, we would consider chunking, taking part of the skill and perfecting that, getting that into the memory and then moving on to another part of the skill, particularly for beginners, and then building up through the complex scenario situation. Because if you take very inexperienced people and you try to teach them a very complex task, they cannot retain it. I think we're actually learning to block out a lot of the information we're given because our brains just reject it. If it makes an engram, it doesn't last. But it is an issue. And there's also this kind of worry that people think, well, you don't need to learn anything because it's all on the internet. I can find it. And that's also almost certainly not right, if I could say that. Yeah. Anybody else?
And the last question from the auditorium, Martin.
Yeah.
Hi.
Hi.
I would like to ask about the repetition in teaching skills, for example.
Yeah.
Is there any data that would support at what time span the repetition should take place? What time should be allowed to pass before we repeat the skill?
Well, there's quite a lot of data on washout of knowledge of skills. For instance, if you teach people CPR and you test them again in 6 months, the majority of the people will have lost about 50% of the information they need. And so theoretically, you maybe should repeat it at 3 months, assuming that it's a linear decline. It isn't. I mean, the Ebbinghaus suggests that it's an exponential decline. And so repeating is probably important within a short period of time of first acquiring the skill. But there are some things we learn that we never forget, like riding a bike. So why can I ride a bike now when I learned when I was 11? And I don't do it very often, but I can get on a bike and ride. So the understanding of why we retain information is very, very poor. But there is definitely, if you test people when they come out of an MCQ, they'll pass the MCQ on the day, and you test them 2 days later, and their scores have really dropped. So we do have a system which we don't understand, which is looking at the information we've got and throwing some away and keeping other bits. Through the consolidation and new dendrites program mechanism, probably, also through the glia, probably. But how we make our information in a form that is less forgettable is not clear at the moment. I'll come back in 5 years and tell you. Okay.
So thank you very much. Thank you, Lesley.
No, finally, I just want to ask, what's this building? It's my hospital. Yes. Anyone remember its name? No, that's him. We're great rivals. University College Hospital. Yes. Thank you very much for your attention. Bye.
Lesley Broomly.